Okay. All right. I've got 8:35, so I'm gonna get started down here. This is COMP2804 discrete structures 2, and I'm Daryl Hill, the instructor. So I did want to show you. I believe there's a link to this on Brightspace, but this is built by people here at Carleton, discretemath.ca, and it has well, COMP2804. I'm not sure if there's anything there. But what they did is they put in a bunch of old midterms and old finals, and you can actually take these. So if I wanted to do the midterm from 2014, it's a multiple choice. I answer the questions and you can get feedback on whether you're right or wrong. So it's a very handy study guide for what's coming up. The other tool is Wolfram Alpha. If you're not familiar with it, it's, well, you can do a bunch of different things in here, but one thing it's really good at is math. So we're going to be taking binomial coefficients. So I can write binomial coefficients in here. For instance, 5, choose 3. And it tells me that's 10. And I can multiply very complex expressions. And so when you're writing your assignment answers, I don't want you to write these answers, but this is good for checking your work, right? To see if, oh, is this actually equal to that, or maybe there's something else you want to check. So these are two very good sites. All right, so today we are here on January 18th. We are going to finish up the product rule, and we're going to, yes, sir. Oh, that's, yeah. Sure. Yeah, go for it. So
hey guys, so I'm Ray from the SSC. I'm a first year representative. You guys didn't hear about us, and did a very bad job the first semester. So our entire job at SSC is to let you know about the events happening in our group, and let you know about mentoring. So mentoring is just a very good opportunity to make sure you're tight with your schedules, with your time management, and that's by going to the Hirschberg 3435, I believe, room where the SSC is located, and scheduling an appointment with a mentor who has taken courses like yours before and done very well in them. And so they can tell you a lot about how to succeed in courses like these. Now, they will not tutor you, but they will give you very good skills or give you good insight on what you should do to succeed. Now, just a few events that are coming up for this week. So this week's actually starts out 2 weeks. So for CS, there are actually a few labs happening today, research labs where you get to go and explore the lab yourself with the professors who run them. So it's a very nice opportunity. It's happening today. So you want to check the site as soon as you can. There's also a using Git part 1. Git is a very important component of computer science, and I think you guys will benefit a lot from attending a workshop like that. And that's happening on January 19th at 1 p.m. at the same room. And also, if you guys are interested in business or entrepreneurship, there is an innovation hub meeting. Now, we are in CS, but there's always a chance of running a business, no matter what your major is. So if you guys are interested in anything like that, or just some information on how to even start with running a business or getting the idea for a business, I think the innovation hub is a great place to start. And that is happening on January 19th at 2:30 p.m. Now, to register for all this, you're going to go on to Carleton Central, and you're going to go to My Success. From My Success, you're going to see assigned student success center tab. You're going to open that, you can see all the events that are happening. And again, this is in 3431, not 35, 31, 33. And yeah, you're welcome to jump by anytime, even just for a quick talk, maybe the mentors, or just to chill. It's your spot too. All right, thank you guys so much.
no problem. Okay. All right. So yeah, today we're going to be finishing off the product rule and then starting on counting. As mentioned, starting this week, the material is going to be, you're going to progress by sort of leaps and bounds in terms of what you can finish on the assignment. I think I'm going to end up using the first question on the assignment as part of the lesson. I don't know if we'll get to it today. But it's useful to illustrate a common problem in counting, which is double counting. And I think a lot of you are instinctively, or at least the people I've talked to, are instinctively doing that question incorrectly. So in both classes, I'm probably just going to use it as part of the lesson, and then You can get free marks if you understand it and can spit it back at me. Yes, the assignment, once we're done this class, you should be able to do the complete assignment, and every class will be, a few more questions. But any questions on the calendar before we get started? Okay. Last class, we had left off just before talking about books on shelves. So what I want to do is first, we can review the product rule. Well, let me see here. I think I went too far. Yeah, so the product rule, in order to use the product rule to count something that's too large to count by hand, I'm going to express as a procedure some sequence of tasks that I would use in some sense to generate that thing or to choose one of those things that I'm trying to count. So for instance, for the, and the other thing we need for the product rule is that whatever choice I make for task number I doesn't affect the number of ways that I can do task I plus 1. And that, that is also true more generally for tasks I minus 1 and I plus 2 and etc. All right, so that if I can express a way to sort of build these things as a sequence of tasks and the number of choice or the way I do task I does not affect the number of ways I can do task I plus 1, then I can apply the product rule. And so we had left off last class talking about putting books on shelves. In this particular example, we had 4 shelves and 5 books. So each task in the procedure is I'm going to place a book on a shelf. But when I place that book on the shelf, I'm not, that's not the only thing I have to keep track of. If there's another book there already, for instance, I put B3 on S3, and then I want to put B4 on S3 as well, then I have to keep track of what order B3 and B4 are in. So I can put B4 to the left of B3 or to the right of B3. Yeah, so that is the problem in a nutshell. The bookshelves are static, but the books I have to place, and I have to keep track of those 2 things. So what happens is that this particular order is different from this particular order. So in this one, even though it looks the same, I've swapped the order of B3 and B4. It's okay to have empty shelves, that's not a problem. And it's okay to have all the books on a single shelf. And in this case, our shelves are infinite, right? So we can put as many books as we like. Although that doesn't sound realistic for books on shelves, there's a lot of problems that we map to that sort of perform exactly like this, where this is true, where you can sort of have infinite things. All right. So that is the problem in a nutshell. Does anybody have any questions on the problem itself? Okay, so we have a procedure in place where our procedure is a sequence of tasks, and it's rather the obvious one. Each task is I put a new book on the shelf. So now it's left to count the number of ways I can do each task. So we'll just look at an example here. We start with empty shelves, and then we place the first book. So B1. Well, I have 4 shelves I can put it on, so I have 4 choices for B1. So N1, which is the number of ways to do task 1, is 4. So let's say, for example, I put B1 here. Now, when I look at where I can place book 2, actually, I have a new spot I can put it. So I can put it on shelf 1, shelf 3, or shelf 4, but I could also put it to the left of the left of book 1 on shelf 2 or to the right of book 1. Right, so in this case, I now have 5 choices for book 2 in this particular example. So let's say, for instance, I put it here on shelf 2 again. Now I have book 3, and now I can put book 3 on shelf 1, on shelf 3 or shelf 4, and now I have actually 3 locations on shelf 2 where I can put it. Okay, so now the number of ways to do task 3 in this particular example is 6. Right. So there seems to be a pattern forming here where each successive task has an additional, we add 1 to the number of ways we can do it. Let's say we put book 3 here. We put book 4 here. So let's say we have book 3 here. I could put book 4 on shelf 1. I have 1, 2, 3 places on shelf 2. I have 1, 2 places on shelf 3, and I have 1 place on shelf 4. Let's put 1 here. So if I add all of those up for book 4, I have 7. So N4 is equal to 7. And then the pattern holds for N5 as well. So N5 is 8. Okay, so we have our sequence of, in this case, 5 tasks. And the first one is equal to the number of ways I could do it is equal to the number of shelves. The second one is equal to the number of shelves plus 1, the number of shelves plus 2, plus 3, and in this case, plus 4. So yeah, that seems to be the pattern. What we want to do is sort of convince ourselves that that pattern holds no matter how we place the books. So let's say, for example, we placed book 1 here and book 2 there on this shelf, but in another iteration, I place book 1 here by itself and book 2 here by itself. So now how many places do I have to put book 3? Well, in this case, I have 6 places, right? I have 1 here, 3 here, 1 here, and 1 here. And on the other shelf, I have 1 here, 2 here, 2 here, and 1 here. So that is also equal to 6. So in general, irrespective of how we place the previous books, the number of ways that I can do my next task seems to stay the same. Right. So, and I think it shouldn't be too difficult to convince yourself that every time I place a new book on a shelf, I'm also in some sense placing a new divider. So I'm adding one more shelf, right? If I define shelf as a single place to put a book, every time I add a book, I also add another shelf, another location. Okay, so it does seem as though we can apply the product rule here because it does fit. Even though these numbers change, it doesn't matter what I choose for the previous I-1 tasks. Task I still has the same number of ways to do it. Okay, is that good? Any questions on that? Okay. All right, so every time we place a book, we split an existing slot into 2 slots. So that's sort of the idea behind it. And this is not quite a formal proof, but it should be sort of rather obvious. So we're not going to do a formal proof. So yeah, we can apply the product rule here, which means that, sorry, one sec. The number of, yeah, so that is I'm not sure when you asked that exactly, but the number of ways is not being affected. Where we can place the books is being affected, but the number of ways is the same. So yeah, that is, we can use the product rule, even though each time we do things a little differently, the numbers all stay the same. All right, so yeah. So for task I, yeah. So in general, for task I, the number of ways I can do it is as follows. So I can either place book I on a shelf on the far left, let's say, and this is not the only way to define it, but it is one way to define it. So for task I, number 1, B3 here, B3 here, B3 here, or B3 here. And or I can place BI immediately to the right of a book that's already on the shelf. Right, so this is one way to define it. And it's a nice, easy way to count. So I have, for the first part, I have n choices, plus I have an additional I-1 choices, because I've already placed I-1 books when I get to task, when I get to place book I. So that means task I has n plus I minus 1 ways to do it in general. All right, does that make sense? Any questions? Okay, so we have a general formula now for the number of ways to do task I. Yeah, no matter what, this always stays the same regardless of how I did the previous tasks. So I can apply the product rule, and the total number of ways is multiplying all of these out. Okay, so what does that give us? Well, it gives us something a little bit ugly. Is it okay to use voice chat for questions? I don't know. I might be able to hear you, but it might be quiet. I would prefer you just use the chat. I don't really have I don't want to mess with the volume because, well, I could try and pipe it through the speakers, but otherwise I don't really pay attention to the thing. So just please type it out in the chat. That would be better. And then I could just repeat it. Okay, so task 1, there are n ways, right? The first book, I have n shelves, so I have n ways to place it. Task 2, I have n plus 1. Task 3, n plus 2. And then when I'm going to place the second last book, I have n plus m minus 2. And remember, our general formula was n plus I minus 1. Well, in this case, my I is m minus 1. So n plus m minus 1 is equal to n plus m minus 2. This is really difficult to keep track of, even when you're well practiced at it. So hopefully this sort of makes sense. But again, a lot of these concepts, and feel free to ask questions, but a lot of these concepts, you need time to have them sort of marinate a little bit, right? You gotta think about them a little while, and then you see them multiple times, and then eventually it starts to, okay, it makes sense. But yeah. So the second last, n plus m minus 2, and the last one, nm is, in this case, I is equal to m, so n plus I minus 1. So these are all of the numbers for all of the tasks that we're going to do to place m books on n shelves. And we're using the product rule, so it's going to look something like this. Okay. All right, so we have an expression, but it's not a very nice one. We have that ... there, and we want a closed form. Again, similar to when we counted the number of one-to-one functions, every time we did a new task, there was one less thing to choose, right? Every time we chose to map A1 to something in the set B, then I could never choose that thing from B again. So every time when I was doing the one-to-one functions, there was one less, and I had this sort of a, what do you call that? It was sort of look like a factorial, right? So, and then to find it, we divided by the first part. So we're going to do something very, very similar here. So we have something that kind of looks like a factorial, except it counts up in this case instead of down, but that shouldn't matter too much. I can always rearrange it to count from the highest to lowest, right? So this sort of looks like n plus m minus 1 factorial, except I have too many of these factors. So I have n plus m minus 1 factorial, and what I want is to express this expression somehow using factorials. So we're going to do exactly the same thing as we did before. I'm going to take n plus m minus 1 factorial, and then I'm going to divide by the part that I don't want, right? So if I, cancel all of these factors out, then what I'm left with is exactly the thing I was trying to express, right? So this expression here, which is n plus m minus 1 factorial divided by n minus 1 factorial, is exactly equal to the the thing I wanted to express. Okay, so then in general, if I have M books and I want to place them on N shelves, I now have a formula, N plus M minus 1 factorial over N minus 1 factorial. It's hard to remember, but you know. Yeah, any questions? Okay. If you're ever sort of in doubt about whether I should do, you know, because sometimes there's a +1, there's a -1. We've seen two different expressions that look like this now. And the other one had +1. So if you plug in a few numbers, you know, I say, well, I have, yeah, if you plug in a few numbers, sometimes it becomes more clear. But if we look at our original example, where we had 4 shelves and 5 books, I can now compute that. So I have 4 shelves, 5 books minus 1 factorial over 4 minus 1 factorial, which is equal to 8 factorial over 3 factorial. So 6,720 ways to place 5 books on 4 shelves. And you don't have to reduce it to this. In this case, this is 6,700 is rather a small number. I don't really need to see if it's a 10-digit number. I don't need to see that. You can leave it in sort of an, you know, whatever form it is. This, to me, shows that you understood what you were doing. If you write a big, long decimal, I have no idea how you got there. You know, if you did not show your work, I have no idea how you got there. And if you make a mistake in the digit, well, I don't know where you went wrong. So if you keep things in their original form and you make a mistake, then we can see where you went wrong and we can help you out. So I would prefer that. Okay, so a review of the product rule. I'm sort of generating something, or I'm counting the ways I can do something. I express that as a procedure, which is a sequence of tasks. And the important part, the choice we make for task I does not affect the number of ways we can do task I plus 1. It might affect which choices we can make, but not the number of choices. Then we can apply the product rule. Okay, so that's books on shelves. Any questions before we move on to subsets? All right, so we have a set here. We've seen this set before. There's 5 elements. We want to count the number of subsets in total for this set S. So here are some examples of what these subsets could be. I have a set which contains A. I have a set of size 3, A, B, C. I have a set of size 2, B, C. And we've seen some examples of this. We actually counted all the sets of size 2, right? Or subsets of S of size 2. And that was 10. We counted them in one of the earlier examples we did. We also argued that if you have 10 subsets of size 2, you also have 10 subsets of size 3. Right? Because every time I choose 2 elements for a subset, I have the complement of that, which I could also say, well, that's a subset of size 3. So every single subset of size 2 also has a corresponding subset of size 3. So the counts are the same. What about subsets of size 1? How many of those do we have in this example? Yeah, we have exactly 5, right? So we can have A by itself, B by itself, C by itself, D by itself, etc. What about subsets of size 4? Yeah, we have 5 as well. And again, the same way that 2 and 3 are complementary, 4 and 1 are complementary because 4 and 1 add up to 5. So if I take A as a subset for size 1, then I'm left with a subset of size 4. So there's, for every unique subset of size 1, there's a unique subset of size 4. Yes, the empty set. We're getting to that. So this is also 5. And then we have the full set itself. course, there's only one of those. So all the subsets of size 5 are 1. And the empty set. Yeah, and there's one of those as well. All right, so subsets of size 0, there's actually 1. So we always count the empty set. Okay, there's nothing in the empty set, but if we count it, it does exist. So it is equal to the number of empty sets is 1. Which means that in total we have, in this case, 32 subsets of S. Okay. All right, so that's rather an awkward way to do it. Yeah, that's fine. This is not going to work if we have very, very large sets. And yeah, so we'll very quickly go through a proof that the empty set is indeed a member of S. So the definition of empty set is, well, if for every element X, this is actually, we should generalize this to say S prime. So the definition of empty set, or sorry, the definition of a subset. So S prime is a subset of S if for all of X in S prime, X is also an S. So every member in my subset must also be an S. That's the definition of a subset. So we want to argue that, well, actually the empty set does fit this definition, right? Even though I'm saying for all elements in the empty set, that element also appears in S. This is sort of a vacuous proof, but you can also prove it by contradiction. If I wanted to prove it by contradiction, I would, since this upside down A is a quantifier, it means for all. When I negate a quantifier, so this is the negation sign. If I negate the quantifier, then I'm going to switch the quantifier. So exists and for all are in some sense opposites, at least in terms of logic, maybe not in terms of English. So I swap the quantifier and I move this negation inside. So the negation of this is X is not an S, right? So this is the quantifier part. This is the what is it? The consequent. So yeah, so this gets negated. So the negation of my original statement is there exists an X that's in the empty set such that X is not in the set S, which is false, right? There is no such element X that fits this criteria. So yeah, this little, again, a little exercise in logic, just to prove that indeed the empty set is a subset of any set, even the empty set itself. All right, questions on that? All right, it's a lot of math for 8:30 in the morning. This is a contradiction. So we counted the number of subsets of size 5, we got 32. But we want to count the number of subsets more generally of a set S with n elements. And we're just going to use the product rule again. So our procedure is we're going to specify a subset. And how we're going to do that is we're just going to start. We're going to look at A1 and we're going to ask ourselves, should this be in my subset? Yes or no? Right. So then I can answer yes or no. I have two choices. So in general task I, I'm just going to take a look at element I and say, is this in my subset? Yes or no. So I have two choices for each of these tasks. Whether or not I've chosen the previous I minus 1 elements does not affect the number of ways I can either choose or not choose to have AI in my subset. So this fits the product rule because the number of ways I do task I does not depend on what I did for the first I minus 1 tasks. Okay, so each element in my set, I have two choices. So my sequence of tasks, I have n of them, and each of them is equal to 2. So yeah, the number of subsets is 2 to the n, right? If I write it out, it's n1 times n2 times up to n small n, which is equal to 2 times 2 times 2, and this is all n times, so I get 2 to the power n. Right. So the number of subsets of a size n in general is 2 to the power n. Yes, it's for all. We can double check our set A, B, C, D, E, which has size 5. We counted 32, and 2 to the 5 is indeed 32. So this, just as a little sanity check to make sure that the way we counted before agrees with the way we're counting now. Again, Wolfram Alpha is a big help when you're doing sanity checks like this, where maybe you take a very simple case and actually plug the values in and see if that agrees with what it should be. But yeah, so it does. So the number of subsets of a size n is 2 to the power n. All right, questions on that? Okie dokie. Okay, the animations got erased. That happens sometimes. But so one thing that we might notice about this, selecting members for a subset is very similar to bit strings. In particular, the way we wrote bit strings, right? So a bit string is just a string of 1s and 0s. Let's say I had bit strings of length 5. When I wrote the bit string, my sequence of tasks was, I'm going to write the first bit. I have 2 choices for that. Then I write the second bit. I have 2 choices for that, and so on and so forth. So the sequence of tasks I defined is actually very similar to this sequence of tasks. I had 5 of them, and there was 2 ways to do each one. So what maybe we want to do is translate from one of these problems to the other. So let's say I have a subset of S, and I want to translate it into a bit string of length 5. Well, I'm going to look at my subset, and if element number I is in my subset, I will write a 1 at location I in my bit string. And if it's not in the subset, I'm going to write a 0. Right, so I'm just going to translate between the tasks. Yeah, so what that means is that for every subset of S, I can map that to a unique bit string of length S. Right, so in this example, S has size 5. A is a subset. Since A is in the set, I write a 1 for the first bit. B, C, D, and E are not in there, so I write 0s for each of those. B0, C0, D0, and E0. This subset here, A, B, D, E, well, A is there, so I write 1. B is there, I write 1. C is missing, so I write 0. D is there, I write 1. And E is there, I write 1. For the empty set, every element is missing, so I'm just going to write 0s for all 5 locations. And for S being a subset of itself, well, then every element is there, so that corresponds to all 1s in my bit string. So yeah, I've defined a function from all of the things that I'm counting, all the subsets of S, a 1-to-1 function to the bit strings of length S, right? Each one is mapped to a unique bit string. All right, make sense? Questions? All right, so now the key here is I actually can do that the other way as well. I'm going to go from a bit string to a subset. So I have a bit string of length 5 in this case. If I read a 1 at location 1, I include A in my subset. In general, if I read a 1 at location I, then AI is in the subset. And if I read a 0, then AI is not in the subset. Right, so now I have a mapping from bit strings. Now this is written completely incorrectly. This should say bit strings of length S mapped to subsets of S. But this is just the reverse procedure from before. I have a bit string 10000. So 1 is there, so I include A in my subset. The rest are 0, so I don't include anything else. 11011. This one corresponds to A, so I write it. This one corresponds to B, so I write it. This 0 corresponds to C, so I do not put C in that subset. And then I have a 1 for D and a 1 for E. So those are in the subset. 0, 0, 0, 0, I lost track. But of course that maps to the empty set, right? I have no elements in my subset. And of course, if I had 1, 1, 1, 1, 1, that would map to S itself. So now I've defined another function going the other way from the set of bit strings of length 5 to the subsets of a set of size 5. And again, this is a one-to-one function, right? Which means that each one is mapped to a unique subset. So what that means, if I have a one-to-one function from A to B and a one-to-one function from B to A, I have what's called a bijection between those two sets, right? So the sets are instances, things that we're counting. And a bijection means that they actually have the same cardinality. They have the same number of elements in each set. So that means the number of subsets of size S is exactly equal to the number of bit strings of length, or sorry, the number of subsets of size N is equal to the number of bit strings of length N. I'm still not sure I said that correctly, but I think you get the picture. Yeah, and what that means is if we count one, we've essentially counted the other. So you can, you might find actually a lot of problems map to not just bit strings, but strings in general. There's a lot of things that you can express basically as strings with different rules. So yeah, in this case, if I solve bit strings, I just have to say, well, there's a bijection between bit strings and subsets. So I don't have to count the number of subsets. I can just use bit strings or vice versa. Okay, questions? All right, so this comes up again and again, and a lot on your assignments. We've looked at a bunch of examples, but the thing is, of course, I don't ask you for those examples on the assignments. I ask you for problems that you have a bijection with things from the lesson. All right. So that brings us to counting. How are we doing? Okay. So now we have the fundamentals, which is the product rule. Now we're going to apply it to slightly more complex problems. So this is very similar to our assignment as well. So I have strings of length 75, and each character in my string is an uppercase letter or a digit. So how many such strings do I have? Right, so I have 26 letters and I have 10 digits. And the string is length 75. So yeah. 36, I have, so each task, so let's say I write my string from left to right, then I have 36 choices for each task. So yeah, you're right about that, but then I have 75 tasks, right? Yeah, so each location in my string, so I'm going to write out a string. My sequence of tasks is write my string from left to right. For maybe I write an A here, a 7 here, Z here, but in each of these I have 36 possible choices, and there's 75 of them. So I have, in this case, 36 choices for each of my 75 tasks, which means that I have 36 to the power 75 number of bit strings in which each character is an uppercase letter or a digit, and there's 75 of them, exactly. All right, good. Questions on that? All right, so this maps pretty much to your first assignment question, which, yeah, very good. Which basically I'm going to burn because it makes a good lesson as well, but yeah. So free marks for anybody who wants it. But let's say that we make a slight adjustment. We have strings of length 75. Each character is an uppercase letter or a digit, and it must contain at least one digit. So we can count strings. That's actually no problem whatsoever. But now we have a problem. When we counted all of the strings, we counted strings that contained no digits. We don't want to count those. So what's one way to do that? Well, let's say that we can look at all of the possible cases where we don't have digits. So at least one digit, well, there's a wide range. I could have 1 digit. I could have 2 digits. I could have exactly 3 digits. I could have exactly 75 digits. So if I wanted to break it down into cases, there are 75 of these cases, which we can count. And we're actually going to talk after we get to binomial coefficients in more detail. We'll talk about how to solve different versions of this problem so that, because it is very common to double count at this point. So I want you guys to, I want to avoid that with you guys. But regardless, 75 different calculations. We could write a computer program to do it, but we can't really compute it ourselves very easily. So yeah, what's another way to do it? Well, we know how to count all of the strings, right? That's pretty straightforward. So now we're using a Venn diagram. So this is the set of all strings, let's say. So each of these dots represents one of these strings. And then what we want is to count, we have a subset of that, which is all strings with no digits. And we want to count everything that's in the green, but not in the blue. Right, that's basically what we want. So we have a bunch here with no digits, and we have a bunch out here with digits, and we just want to count the ones in the green. So how we can do that is actually, we can count the complement of the set we're looking for, right? So the complement of all strings with at least 1 digit is all strings with no digits. So this is what I want to exclude. And it seems like maybe I can count that easier, right? So how many strings of length 75 have no digits? Yeah. I'm not sure. Yeah. To be honest, for the assignment, so question 1A is straight up, I think, right? It's no, yeah, just you can, in that case, you can just write the answer. Because basically the product rule, even though you're just learning it now, as you get practice, it should be sort of second nature to count these sorts of things. So you're going to see the other parts of it, you will have to do a little more work, but in terms of the product rule, you don't have to lay out all the tasks all the time. You can just explain in English. Each character, I have 36 choices or whatever it happens to be. Yeah, that's fine. Other questions? Okay. All right, so we wanted to count all of the strings with at least 1 digit. We don't want to count these ones, but we can do some simple math. Oh yeah, this was a question I asked. So yes, if I wanted to count all of the strings with no digits, I'm just going to exclude the 10 digits. So now each character I write can be one of the 26 letters. I have 75 letters to write down. So it's 26 to the power 75 is the number of elements in this blue subset, right? Makes sense? Questions? Okay, so yeah, so this is what we want to count. We want to count all the green. We can count all of the green and blue together, and we can count the blue by itself. So what we're going to use is what's called the complement rule. Right, so I'm going to count the number of strings total and then I'm going to subtract this blue region, which is all of the strings with no digits, and that will give me an accurate count of the green region. Okay, so all strings with at least one digit is all of the strings minus all of the strings with no digits. Right? Okay, does that make sense? Nice and simple. Okay. This is known as the complement rule. More generally, we apply the complement rule. Well, this is what we call the green area we call the universe, or sorry, the green and blue together, generally speaking, when we're talking about sets. We call this the universe. Universe backslash A, this is set difference. So the green is the universe minus all of the stuff in set A. This can also be expressed using set builder notation. So this is a predicate. What this means is this set consists of every element X, where X is in the universe, and X is not in the set A. Right, so these are all different ways to express the same set. So we use the complement rule in general if we want to count A, but it's too difficult. Just there's too many cases, it's too complicated. But if we look at the complement, maybe we have a very easy time counting the complement. Right, so this is sort of, this diagram here is sort of the inverse of what was on the previous slide. I actually want to count A, I want to count the blue, so I'm going to, but I don't have an easy way to do it. So I'm going to count everything in the green and blue and subtract the green, regardless of what your mental model looks like. I think the idea behind it is sort of easy. And this is equal to, we could also write this as the universe minus A bar, which is A complement, right? So these are all equivalent. Okay. So that's known as the complement rule, and we use it if counting a set itself is too painstaking, but the universe is easy, and the complement of A is also easy. Okay. We represent, yes, you can. All right, so the next rule we're going to look at is called the sum rule. And this is, again, we're going to look at Venn diagrams. There's a little excitement for you this morning. So we have our universe, and we have two sets A and B. And what we want to count is the union of A and B. In this case, A and B are what's called disjoint. What that means is that, right, I have a bunch of elements in A and a bunch in B, but there are no elements that are in both A and B, right? So that means they're disjoint. So if I count, in this case, I have 4 elements in A, and I also have 4 in B. So the union of A and B is 8. Simple enough. It's the sum rule. If they're disjoint, I just count everything in one and count everything in the other and add them together to get the union. Right. And when I say the union of two sets, what this corresponds to in English is usually or. Right. So if I say, in this case, find all strings of length 75 or 76. Well, then A might be all of the strings of length 75, and B might be all of the strings of length 76. And when we say 76, we mean exactly 76, not up to 76. So a string can either be exactly 76 or exactly 75 or some other length. But the main thing is it can't be both 75 and 76 characters long. It has to be one or the other. So these are disjoint sets, right? So if I said A was all strings of length 75 with characters and digits, and B was all strings of length 76 with characters and digits, then I can apply the sum rule. So A plus B. A is 36 to the power 75. B is 36 to the power 76. Right. Again, we're using the product rule, but I'm sort of glossing over it. I write the characters in B from left to right. There's 76 of them. Each of them, I have 36 choices. All right. So questions? Okay. Yes. So this is also known as pairwise disjoint. We'll get into what this means a little more later. And if I have 3 sets, that also applies as long as they're disjoint, right? So there's no overlapping. Each of them has their own members. So A union B union C is equal to the size of A plus the size of B plus the size of C. So let's look at a more complex example for this. All strings of length 75 or 76 or 77. We know these are disjoint because this is precisely 75, 76, or 77. So it can't be both. So now we're going to apply the sum rule. The extra twist is that each of them is composed of digits or uppercase letters, and there must be at least 1 digit. So now I'm combining rules a little bit, right? So if I wrote this in my Venn diagram, I could say, well, I could divide my universe into all strings of length 75, all strings of length 76, and all strings of length 77. And these are at least 1 digit. Right? And we know how to count that. It's actually complicated to count it directly, but we can use the complement rule. So I'm going to take all of the characters of length 75. So yeah, let's say A union B union C is equal to, well, the size of A is 36 to the 75 is all strings of length 75. And then I'm going to subtract all of the ones with 0 digits. Right? So if it has no digits, every character is 26 choices instead of 36. Plus counting B, well, in this case, I have 36 choices for each character, and it is 76 long. All of the strings with no digits are 26 to the 76. And the size of C, 36 to the 77 minus 26 to the 77. Okay, so then in this case, I'm using the sum rule and the complement rule together, but it's still kind of simple. But yeah, questions on that? Yep. Sorry? Yeah, so at least 1 digit in the string, yeah. Okay, so yeah. So yeah, digit means 0, 1, 2, 3 up to 9. So there's 10 of them. Yeah. Yeah. Yeah, I would prefer if you left it like this. Again, if you expand this out, you're going to have a big number that's almost meaningless to me. But here we can see sort of exactly your process. Yeah. Yeah. To count, to say that there's at least 1 digit? Yeah, okay, so this is a common one. Let's talk about that with, let's say our strings are length 5. So what you're going to say is I want to count all of the strings with at least 1 digit. So I'm going to put 1 digit here. I have 10 choices. Okay, but I also have strings with 1 digit where the digit is there, and the last one is a character. So if I fix the location of my digit, I'm not counting all possible strings. Yeah. Okay. but I also have to count where I can put that digit. So again, I'm going to burn a little bit of what's in your assignment. Let's say we wanted to count all of the strings with precisely one digit. Yeah, all right, perfect. So let's say I have strings of length 5 with precisely one digit. So I'm just going to adjust the product rule a little bit. So the sequence of tasks, the first one of the tasks is going to be to choose a digit. So I have 10 choices. So let's say I do that first. So task 1, I have 10 choices, and then I need to place it somewhere. So I need to choose where it goes. So let's say I have, in this case, they're length 5, so I have 5 places. So 10 times 5 chooses a digit and puts it somewhere. Okay. And then I have 4 locations left where I can choose characters. So I have 26 choices for each of those. 6. Well, I'm saying exactly one digit in this case. Because this is, if I do this for at least one digit, I will overcount. I'll explain that right now, actually. But so this is precisely one digit. That's the number of ways. I choose a digit, I choose the location, and then I choose the other 4 characters wherever they happen to be. Okay. Let's say I did this exact procedure and I said that, well, that counts all that are at least one digit. Okay, so I choose a digit, I choose 2, I choose a location, I choose the first location, and then I choose, what you want to say is, well, I just choose whatever for the rest of them. Okay, so I choose 2, 2, 2, 2, and 2. So I've counted this string. Now I'm going to do the same procedure, but I'm going to make different choices. So I choose a digit. Well, I still choose 2, but I'm going to choose a different location. I'm going to choose the last location. And then I'm going to, for my other 4, I have 36 choices. I also choose 2. So this is a different task, but it's counting the same string. Okay, so this is a good lesson in how not to do this. A very common pitfall when you're starting out with this stuff. Repeating locations. Again, so there's lots of actual different questions I could ask. I could say, well, there must be one digit and it has to be in the first or last location. Well, then when I place my digit, I just have 2 choices. Right, so there's lots of different questions to be asked. I will go over, because this is from your assignment, the one common problem. I can extend this. What if I said I have strings of length 5, exactly 2 digits? So I'm going to show you what not to do. And then later when we take binomial coefficients, I will show you how to solve this problem. Simply because I don't want the, I feel like a lot of people are making the same mistake. So exactly 2 digits. My task 1, let's say I choose 2 digits. So I have 10 ways to choose digit 1, 10 ways to choose digit 2, and now I'm going to place them. So digit 1, I'm going to place, and let's say I choose 2 and 3 here. And then I have 5 locations for digit 1 and 4 locations for digit 2. So let's say I place 2 here, 3 here. And then I have 3 characters. So this is times 26 to the 3rd. Okay, so that is my procedure. I choose the 2 digits, and then I choose location for digit 1, and I choose a location for digit 2. I choose the last 3. So where do we go wrong here? Well, let's say I chose digit 1, I chose 3. Digit 2, I chose 2. And when I go to place them, I just choose in the reverse order again. So number 3, I put in the second location, and number 2, I put in the first. So now I have the same 2 digits in the same 2 places. These are 2 different tasks, or sorry, 2 different things that I've counted. I've counted this, I've double counted all of these strings. All right, so the sort of the rule of thumb, the easy way to remember is if you do pick and place for more than one thing, then you're going to be double counting. Right, so the solution to this is, well, the easiest solution is to pick my two places at once. Right, so when I pick my two locations, I could pick 1 and 2, or I can pick 2 and 1, but I'm really just, those are the same thing. So I'm double counting that. So what I want to do is I want to count the number of ways I can choose two locations where I don't think about the order. Right, so this is where binomial coefficients come into place, because if I do 5, choose 2, that is exactly the number of ways I can choose a subset of size 2 from a set of size 5 where the order doesn't matter. Right, so if I did this in order, I have 5 choices for the first location and 4 for the second. This is equal to 20. But 5 choose 2 is actually equal to 10, so I'm not double counting in this case. Right, so if you do pick and place more than once, you are in danger of double counting. So this, again, we're going to get into more examples, and hopefully at some point, if it's not, the light bulb's not on right now, it's going to come on a little later on. I did want to warn you about how not to do it so that you don't make a mistake on your assignment that you forget to fix later. But any questions on that? Oh, yeah. Yes. So there, again, and there's multiple ways to count things, but sure, if I was going to solve this problem, I could use the product rule, choose digit 1, choose digit 2. Actually, no, the correct order would be I choose 2 locations, choose digit 1 for the first location, and digit 2 for the second location. That way I'll never end up double counting that, because, yeah. And then I choose my, in this case, 3 characters, so 26 to the 3. So a string of length 5 with characters and digits and exactly 2 digits, this would be the answer. Again, I'm sort of burning this one off the assignment. I'm just going to give you the answer because it's an important lesson. It's an easy mistake to make. Yeah. Uh, 5-3, sorry. I have, that is the number of ways to choose. I have 5 locations where I can put characters or digits, and I'm going to choose 2 of them to put my digits in. Yeah. And it's also equal to 5 choose 3, right? It's the same thing. So whether I choose 2 locations for my digits or 3 for my characters, doesn't matter. Questions, other questions? All right. So that's a lot of stuff that, yeah. Anyway, we will get into the more specifics of binomial coefficients, and hopefully that will make more sense. But for now, make sure you don't do pick and place. That will double count. But yeah, using the complement rule and the sum rule here, we get this. So a more generalized version of the sum rule, okay, is called inclusion exclusion. So again, I have a universe and I have 2 sets A and B, but now A and B have some elements in common. Right, so let's say I have 5 elements in A, and I also have 5 elements in B. And if I tried to count A union B using the sum rule, it's the size of A plus the size of B is equal to 5 plus 5 equal to 10. But I actually have 8 elements in the union because 2 of them are in both sets, right? So when I counted A and B, I counted this one, this one, this one, this one, this one. And when I counted B, I counted this one, this one, this one, this one, and this one. So the ones in A intersect B, I've counted twice. Okay, so the solution to that in order to count properly is that, yeah, I count those twice with the fancy animations, and I'm going to subtract it in order to get a correct accounting. Right, so these guys, I counted twice. These I counted once. So if I subtract these two, then I get the correct accounting. So this would be equal to 5 plus 5 minus 2 equal 8. Okay, so that's inclusion, exclusion. Questions on that? Okay. So as an example, we're going to count bit strings. So again, these are strings of ones and zeros, not the full alphabet like before. All that means is that when I write out a bit string, I have two choices for the characters, right? So I write a 0 or a 1. So yeah, I have a set A, all bit strings of length 75 that start with 10101, and a set B, all strings of length 75 that end with 1100. Right, so those are my two sets. And then you'll notice that, well, even though I don't have them explicitly here, there are strings that start with 10101 and end with 1100. So when I counted A and B, I double counted all of these strings. Right, so I can't apply the sum rule, so I'm going to apply inclusion, exclusion. Now, to count A, I have 5 bits that we call fixed, which means that I basically have one way to write them. Or another way to put it is I have no choices in the matter. 10101, those are written down for me. I don't get to choose. What I do get to choose are the 75 bits that are left. So my product rule, my sequence of tasks are to write 70 bits starting at location, let's say 6. Right, so 6 up to 75. There's 70 of those, so I have 70 tasks. So the size of A is equal to 2 choices for each of them. Oh, sorry, not 75. 2 to the 70. Right, so I had 70 bits that I have a choice in how I write them. 5 bits of my 75 are fixed. Those are chosen for me. B is similar, except in this case, I have 4 bits. They have to be 1100. So I do not have any choice in writing those down. The last four bits are always that, but the previous 71 bits, I have to choose a 1 or a 0 for each of them. So size of B is 2 to the power 71. So now A intersect B, let's write that here. Another way to think of, so this is the intersection of two sets, and this corresponds to an English and, right? So when I say A intersect B, I mean all bit strings of length 75 that start with 10101 and end with 1100. So now I have 5 bits here that I have no choice in, and I have 4 bits here that I have no choice in. That is 9, and then in the middle I have 66 bits where I have to choose a 0 or a 1. So to subtract A intersect B is 2 to the 66. Okay. All right. So that's A union B using inclusion, exclusion. Questions on that? Okay. I think we determine them individually. So I get this question too. This is just another way to compute it. I have strings of length 75, but 5 of those bits I no longer have a choice in. So this is just another way to write it. Just another way to write 2 to the 70. It's neither right nor wrong, but you know, some things make more sense to some people and others to other people. So yeah, this is another way to write all of those things. I subtract the number of fixed bits from the exponent. And I get, yeah, the same answer as before. Okay. This still applies. How much time do I got? Yeah, 10 minutes, perfect. So this still applies. Inclusion, exclusion actually is encompasses the sum rule. So let's say, for instance, that A and B are disjoint, which means they have no elements in common. And I try to use inclusion, exclusion. Well, that's fine, because this A intersect B has size 0. So inclusion, exclusion will still give me the correct answer. Right, so it's the sum rule is useful, but you know, if I wanted to be precise, I can always use inclusion, exclusion. Yeah, it's a generalization. All right. Finally, let's talk about 3 sets all intersecting. So I want to count A union B union C, but they all overlap. So I have a bunch of different regions here, and we're going to see what happens when we count A plus B plus C. Well, if I count everything in A and everything in B, well, we know I've double counted all of this stuff here. Oops. All right. And I've also counted, well, I've counted this and I've counted this. So that means I've double counted everything in here also. And I've counted A and I've counted C. So I've double counted everything in here also. And what happens is that I've actually triple counted everything that's in the intersection of all 3, right? So, yeah, so I now have a more complex region. Let's skip ahead a little bit. This is what I just explained, that all of these other regions I count twice, and A intersect B intersect C, I count 3 times. So yeah. So let's start by using our inclusion exclusion that we know. I'm going to add A plus B plus C. I know I've double counted everything in these regions, so I'm going to subtract them. All right, so that's standard inclusion exclusion, but let's see what happens to our counts. So this is the number of times I've counted things in each region. So yeah, A plus B plus C gives me this diagram. Now I subtract A intersect B. So I'm going to count this 1 less and this region 1 less. I subtract B intersect C. I'm going to count this 1 less and this 1 less. And I subtract A intersect C, and I count this 1 less and this 1 less. Okay, so now if I look at the number of times I counted each region, this is correct, this is correct, this is correct. These are of course correct. This is now 0. So now I've undercounted the intersection of all 3. Okay, so this is what my current, the number of times I've counted each region looks like. So what I'm going to do is I'm just going to add A intersect B intersect C back in. Right, so I get this inclusion exclusion is I add all of the original sets, I subtract their pairwise intersections, and then I add back the intersection of all 3. And then I have a correct, each region is counted exactly once, and this is the correct, this should be union. But yeah, this is A union B union C counted correctly. Okay. Questions? Okay. We can also do it with 4 sets or 5 sets or 6 sets. We're not going to get into that because it's kind of messy, but if I did 4 sets, I would add the original sets together. I would subtract all of the pairwise intersections. In this case, there are 6 of them. I would add all of the intersection of threes. So there are 3 of those, or sorry, 4 of those, and then I would subtract. Sorry, I would subtract the intersection of 4 sets. So I can generalize that as much as I want to any number of sets. I just alternate adding and subtracting as I, get higher and higher in the number of intersections. And the number of these starts to look like Pascal's triangle, which we haven't gotten to yet, but it grows pretty quickly. Okay, how are we doing? 5 minutes. Questions on that? Yep. Sorry, I didn't quite catch that. Why are?
That example, if we have the A and C, then you have to go on like trying to get A, then that you said when it's two pairs, and then why are you again adding like subtracting one that kind of add same set?
Yeah, so I'm not going to prove it for 4, but basically what happens is the same thing, is that at first I overcount when I count the original sets. When I subtract, now I'm undercounting. Then I add the next set of intersections, I'm overcounting again. And then it's not till I get to the intersection of all that I'm not going to prove for this, but it's the same thing that we did with the 3 sets, where we counted what happened every time we added a new thing or subtracted a new thing. Every time you either overcount a little bit or you undercount a little bit. So to get precise, you have to do this. But we're not going to, sorry. We're only going to go up to 3. So 3 is all you'd have to worry about ever anyway. But this is just a nightmare to go 4 and above. Sorry, did that answer your question? Yeah. Okay. 3 minutes. We might be able to. This should be sort of simple. Let's say we have 3 sets A, B, and C. These again are bit strings of length 75. A starts with 10101. B ends with 1100, and C has 101 in the middle. Okay, so we can count each of these individually. So I would want to count the union of all of these. I'll go through it rather quickly, but if I write out my formula, B plus C minus A intersect B minus, actually, I think if I go to the next slide, that's written out for me. Yeah, nice. Okay, so to count A, well, we've counted that. It is 2 to the 75. Counting B, 75 minus 4 is 2 to the 71. And C, 75 with 3 fixed bits is 2 to the 72. Minus A intersect B. A intersect B has 9 fixed bits, so that is 2 to the 66. A intersect B has 8 fixed bits, 2 to the 67. And then B intersect C has 7 fixed bits, so 75 minus 7 is 2 to the 68. And then finally, I look at the intersection of all 3. So I have 5 fixed bits plus 4 fixed bits plus 3 fixed bits. Those are 12 fixed bits. 75 minus 12 is 2 to the 63. Oh, sorry, and this is added back in. So plus A plus B plus A intersect B intersect C. All right, so very, very quickly in a simple example using inclusion, exclusion with 3 sets, that would be our answer. So yeah, that's it for today. We will pick up next class. Oh, A is 2 to the 75 because I made a mistake. Should be 2 to the 70, yeah. Thank you, yes.
I have a question. If I have a stream of number, is there any way except pixel to find the largest value in this stream of numbers?
Yeah, you can just look through one by one, right?
Let's see one by one. Is there any formula, some ways to compare each number beside
Sorry, yeah, I think you should be able to do up to question 4 or 5, but you got to be careful with one. We don't have all the answers for that yet. So is there a way to what? Sorry?
is there a way to like this